Now, let's turn our attention to one of the most important concepts in chemistry, the mole and molar mass. These ideas are absolutely central to understanding how chemists count and measure substances at the atomic and molecular level. First, why do we need the concept of a mole in the first place? Think about atoms and molecules. These particles are unimaginably small. A single atom of carbon, for instance, is far too tiny for us to weigh or count individually. So, chemists needed a way to breach the microscopic world of atoms and molecules with a macroscopic world of grams and liters that we can actually measure in the lab. That breach is the mole. Now, this is where molar mass comes in. The molar mass of a substance tells us how many grams 1 mole of that substance weighs. First, let's talk about Avogadro's number. It is often written as capital N sub A. By definition, Avogadro's number is the number of atoms in exactly 12 grams of pure carbon-12. That number is incredibly large, 6.022 times 10 to the 23rd. This means that in 12 grams of carbon-12, there are 6.022 times 10 to the 23rd atoms. And we call this huge number 1 mole. So what exactly is a mole? A mole is a counting unit, which is written as MOL. Just like we use the word dozen to mean 12, we use mole to mean 6.022 times 10 to the 23rd, which is also called Avogadro's number. For example, 1 dozen apples means 12 apples. 2 dozen apples means 24 apples. In the same way, 1 mole of atoms means 6.022 times 10 to the 23rd atoms. And 2 moles of atoms means twice as many as 6.022 times 10 to the 23rd atoms, or 1.2044 times 10 to the 24th atoms. Take note how similar the logic is between dozens and moles. The only difference is the size of the number. A dozen counts 12 things, but a mole counts 6.022 times 10 to the 23rd things. Why such a big number? Because atoms and molecules are unimaginably tiny, so we need a very large counting unit to connect the microscopic scale with quantities we can weigh in grams. And just like dozens can apply to anything like apples, eggs, and pencils, moles can apply to anything as well, atoms, molecules, or even ions. For example, 1 mole of oxygen molecules contains 6.022 times 10 to the 23rd oxygen molecules. Now that we understand what a mole is, let's apply it to a real chemical compound, calcium nitrate, written as CaNO3 First, let's break this compound down to the atomic level. 1 formula unit of calcium nitrate, CaNO3 contains 1 calcium atom, 2 nitrogen atoms, and 6 oxygen atoms. The formula tells us everything. We see the Ca, which stands for calcium, with no subscript. So that means 1 calcium atom. Then we see NO3, the nitrate group. And the subscript 2 outside the parentheses tells us that there are 2 nitrate groups. Each nitrate group contains 1 nitrogen atom and 3 oxygen atoms. So, if we multiply that by 2, we get 2 nitrogen atoms and 6 oxygen atoms in total. That's the breakdown for just 1 unit of calcium nitrate. But remember, in chemistry, we rarely deal with just a single unit. We usually talk about macroscopic amounts, which means we measure in moles. So let's scale this up. If 1 unit of calcium nitrate contains 1 calcium atom, 2 nitrogen atoms, and 6 oxygen atoms, then 1 mole of calcium nitrate, which contains 1 mole of calcium atoms, 2 moles of nitrogen atoms, and 6 moles of oxygen atoms. This is the key idea. The subscripts in a chemical formula tells us not only the ratio of atoms in a single unit, but also the ratio of moles in a mole of the compound. It also implies 1 mole of CaNO3 contains 6.022 times 10 to the 23rd calcium atoms, 2 times 6.022 times 10 to the 23rd nitrogen atoms, and 6 times 6.022 times 10 to the 23rd oxygen atoms. So, moles allow us to easily scale from the microscopic world of single atoms and molecules up to amounts we can measure and use in the lab. The chemical formula gives us the atomic ratio. By applying the mole concept, we can calculate exactly how many moles of each element are present in 1 mole of the compound. This becomes very important in chemical reactions because it tells us how many atoms and moles of each element are available to react. Let's do some practice problems. How many calcium nitrate units are in 0.250 moles of calcium nitrate? We start with what we are given, 0.250 moles of calcium nitrate. By definition, 1 mole contains Avogadro's number of particles, which is 6.022 times 10 to the 23rd. So we multiply like this. The moles cancel, leaving us with calcium nitrate units. The result is 1.506 times 10 to the 23rd calcium nitrate units. So, in just 1/4 of a mole, there are still an astronomically large number of formula units. Let's move to the next question. How many oxygen atoms are in 0.250 moles of calcium nitrate? First, recall the chemical formula CaNO3. 1 mole of calcium nitrate contains 6 moles of oxygen atoms. So, if we have 0.250 moles of calcium nitrate, the moles of oxygen atoms can be calculated like this. But since we are asked for the number of oxygen atoms, we need to convert moles to oxygen atoms using Avogadro's number. Take note that we used 2 conversion factors in this problem. The moles of calcium nitrate cancel, and the moles of oxygen atoms also cancel, leaving us with a unit which is oxygen atoms. So the answer is 9.033 times 10 to the 23rd oxygen atoms. Here are 2 additional problems. Pause the video and try them on your own. You can use the same method that we just practiced. The answers are as follows. Let's talk about molar mass. Molar mass is defined as the mass in grams of 1 mole of a substance. To help us understand this, let's start with something more familiar, apples and plums. Suppose 1 apple has a mass of 115 grams. If we take a dozen apples, that means 12 apples. The total mass will be 1,380 grams. Now let's compare this with plums. Suppose 1 plum has a mass of 55 grams. If we take a dozen plums, the total mass will be 660 grams. So both apples and plums have the same quantity, a dozen. But the total mass is very different depending on what the dozen consists of. A dozen apples is heavier than a dozen plums because individual apples are heavier than individual plums. Now, let's extend this idea to chemistry. In chemistry, instead of using a dozen, we use the term a mole. 1 mole of anything contains 6.022 times 10 to the 23rd particles. This is Avogadro's number, and it works for atoms, molecules, ions, any type of particle. For example, 1 mole of carbon atoms contains 6.022 times 10 to the 23rd carbon atoms. The mass of 1 mole of carbon is 12.01 grams. We can also say the molar mass of carbon is 12.01 grams per mole. On the other hand, 1 mole of oxygen atoms also contains 6.022 times 10 to the 23rd oxygen atoms, exactly the same number of particles as carbon. However, the mass is different. 1 mole of oxygen atoms has a mass of 16.00 grams. So the molar mass of oxygen is 16.00 grams per mole. Both atoms have the same quantity, a mole, but a different molar mass. So here's the key point. Just like apples and plums, where a dozen refers to the same number but gives a different total mass, in chemistry, a mole always refers to the same number of particles, 6.022 times 10 to the 23rd. But the total mass depends on what kind of atoms or molecules we are talking about. Carbon atoms have a lower molar mass than oxygen atoms, just like plums are lighter than apples. In summary, a mole gives us a way to count atoms in bulk, but molar mass tells us how heavy those atoms are when we collect them in groups of Avogadro's number. Let's do some practice problems. The molar mass of oxygen atom is 16.00 grams per mole, and the molar mass of carbon atom is 12.01 grams per mole. What is the molar mass of carbon dioxide, or CO2? Since a carbon dioxide molecule is made of 1 carbon atom and 2 oxygen atoms, the molar mass of CO2 is equal to the molar mass of carbon atom plus 2 times the molar mass of oxygen atom. So the answer is 44.01 grams per mole. The next question is very similar to the one that we just finished. Pause the video and try it on your own. The answer is 164.10 grams per mole, which is the molar mass of calcium nitrate. Let's move to the last problem. The molar mass of water is 18.02 grams per mole. Calculate the moles of 32.25 grams of water. In this problem, the molar mass of water will be used as a conversion factor. Mole is denoted by lowercase n. We start with what we are given, 32.25 grams of water. Multiply it by the correct form of conversion factor that converts grams to moles. Now, the answer is 1.790 moles of water.